I'm going to start by talking about black hole thermodynamics, but there's a reason I wanted to call it Spacetime Thermodynamics instead, because black hole thermodynamics makes it sound like we're going to be saying something that's very special to an exotic sort of object that you have to build Lego or something to see. And I think the real lesson of the subject of black hole thermodynamics, where it's going, is that it's telling us something that's true about the statistical mechanics of space-time itself. So ideally, this is something that's really been an idea that's inspired me. We should always view the results about black hole entropy and so on from the perspective of what is this telling me about everywhere. So with that having been said, I am going to start with black holes. I understand I should be using white chalk. So we have black holes, and there's two facts about them which are in striking intellectual tension or some sort of paradox whose implications have not been completely resolved. And one of them is that black holes have event horizons. And the other one is that black holes behave like thermodynamic systems, as if they were lumps of coal or something that have a temperature, but simpler. And yet, we also know in GR there's an interior, and at least classically, information that falls into the black hole does not escape. There is a lot of evidence this is no longer true in full quantum gravity. So it's a fertile field for testing ideas about physics. So we have, before getting into the details, the three most fundamental thermodynamic quantities that a black hole possesses are its energy, which equals its mass by Einstein's most famous equation, E equals m when C equals 1. I also set K Boltzmann to 1 because it is. Okay. The temperature of a black hole is given by, it's proportional to something called kappa, which is the surface gravity. Which, if you do physics 101 mechanics, the surface gravity of the Earth is just that 9.8 thing, but it's, there's a different, more formal definition we'll use for black holes. And
I think it's important to note that in this formal definition is a redshifted surface gravity, right?
yes, that, I'm gonna talk about killing symmetries in just a moment. So it's and there's an entropy that's given by the area over 4gh bar. Okay. So the energy one is sort of obvious because we know that in general relativity, gravity can be measured using a boundary quantity out at infinity called the ADM mass. So for that, for this one, we don't even need to think about quantum mechanics. This is just true classically. So for the temperature, to derive the temperature, we have to start thinking about thing, quantum field theory in curved space-time, and to derive the entropy, we need to start thinking about the back reaction of those fields, or more subtle things like path integrals. Okay, so let's start with temperature. Temperature in statistical mechanics is fundamentally an equilibrium notion, if you think of it like some sort of Gibbs state. So, to talk about the temperature of a black hole, we want to talk about a black hole that is itself in equilibrium, and that is described by the notion of a killing horizon. So I'm going to now define what's called a bifurcate killing horizon. Okay, so we need to define the killing vector. So a killing vector is a special type of diffeomorphism vector, something that pushes the points around, but in such a way that the metric doesn't change. It's an isometry. So the killing vector is defined by saying that the variation of the metric, which is given by the Lie derivative, the covariant derivative of the vector that you use to push points around, symmetrized, that this is equal to 0. So the killing vector has the property, so if you think about what this would do locally to a point, if the anti-symmetric part of this has 6 components in 4 dimensions, and that's the thing that is associated with the Lorentz symmetry of the metric that therefore doesn't change the metric. The symmetric part that has 10 components is the part that does change the metric, and so that's the part that needs to vanish. This is more equations than you have parameters in the vector, so usually you don't have these things. You only have them when there's symmetry. So in Minkowski space, there's the 10 of them associated with the Poincare group. If we have a black hole, there's less of them. For example, for a rotating black hole, like Kerr, where the null, the main ones we want to think about are the time translation one and the angular symmetry that pushes it around. So if, for example, we had if, for example, we have a coordinate system that has a time and a phi coordinate, so that's like this, and then we have some other angular coordinate and some r coordinate. These coordinates are symmetrical, so we can construct killing vectors as linear combinations of the time translation or the rotation. And there's one particular one that is special, which is the one where we take chi a is equal to a unit time translation defined at infinity plus the angular velocity times the unit coordinate of the rotation. So this has the property that although it looks like it involves a translation and a rotational twist out at infinity, when we go up to the horizon, this is the thing that is going to push you along the null directions of the horizon. So we now define the bifurcate killing horizon is I guess I don't have room to write this, I'll put here. Bifurcate killing horizon well, maybe I should start by saying a Killing horizon, h plus or minus, is a future or past, depending on whether it's plus or minus, null surface, codimension 1 null surface in the space-time, whose null generators are ruled by the Killing vector. Okay? So the if in some situations you may just have a past or a future one, but usually when you look at a maximally extended Penrose diagram of a black hole, there's also a bifurcation surface is the union of the past and future Killing horizons. And this is a point that, or a codimension 2 surface that is fixed by the Killing. It's a fixed set of points under the Killing symmetry. Okay, so the whole bifurcate Killing horizon of, for example, Schwarzschild, if I draw the Penrose diagram like this, then what it does is at infinity, it looks like since this is Schwarzschild, we are not including this angular velocity piece. At infinity, it looks like a time translation, but at the bifurcation surface B, it looks like a Lorentz boost. Up here on the future Killing horizon, it just pushes it up, and it's the same on the other side, only the other direction, and it becomes space-like inside. Okay, so now, yes?
What is a future or past null surface?
Oh, yes. It's in relation to the, well, in this case, this is a black hole horizon and this is a white hole horizon, so it's obvious here. More generally, I guess if we can reflect these two sides, then there's no obvious. We would reflect this notion. But what we could say, and we could certainly say that this is a causal horizon with respect to the right-hand side, a future causal horizon with respect to this right-hand one, and a past causal horizon with respect to the other one. But that would be circular, since that would involve acausality in my talk, since I'm going to define future and past causal horizon later. Well, I think at this point, the least embarrassing way out is to define it with reference to the picture. It's this one. See, this is H plus and this is H minus. But H plus extends down here and H minus extends up there. Yes?
I have sort of a dumb question about the Wallace answer. So I assume that you just send a particle inside the black hole?
Sorry, I didn't even talk about particles yet. I just have a black hole, and the black hole has a gravitational field. And if, for example, you had a planet orbiting very far away, and you use Kepler's laws of orbits, you could figure out what the mass of the thing in the middle is.
No. I assume that you have a black hole. Inside the black hole, you have two different black holes.
Okay.
Inside one of them, you have a particle which you just leave inside the black hole, it reaches a singularity, right?
Okay.
But in the second one, the particle starts oscillating until it reaches a singularity.
Okay.
So, do these two black holes have the same energy?
It's not, that's really an ambiguous question, because when you write down a solution to the Einstein's equation to have matter, you don't just need to tell me where the matter is, you also need to tell me how gravitational fields come out of it. So if I start with a black hole and then I perturb it by, for example, adding a shell of mass around the black hole, you have to tell me whether when you add the shell, you're adding more energy to the ADM mass or whether you're taking energy away from the black hole. It's just two different solutions. It's just like if you said, if I added if I have an electron to the vacuum, where does the electric field go? Well, there's different states where the electric field goes in different directions. Okay, so we can now define the surface gravity. So the motivation for the definition I'm about to give is that the surface gravity looks like a boost at the bifurcation surface, and actually it looks like if we ignore the fact that it translates points, it looks like a boost on the killing horizon itself. So we just need to find out how big how much its magnitude is. So if I can write this like this, where what I mean by that, this is the absolute value of the derivative of the killing vector, by which I mean, if you really want me to be precise, I mean this. Where, because this looks like a boost, there'll be like a Tx antisymmetric piece. The derivative of the killing vector will have a Tx antisymmetric components, and this minus the 1/2 is to just take into account that there'll be two ways to contract it, and the minus is just because there's a minus sign when you contract in times. So, but there's a key point of this definition, which is this is when chi A is normalized at infinity. If I don't specify how the killing vector is normalized, I don't have a well-defined number. And my normalization rule is this one, that it looks like a unit time translation at infinity. In other words, another way to put this is if you're an observer living very close to the bifurcation surface, then from your perspective, the killing vector just looks like a boost. And for all you see locally, you could, if you were calculating the Unruh effect or something, you could just always normalize it the same way. The black hole will end up looking like it has different temperatures because there's a relative normalization difference between the unit boost and the unit time translation. So near the horizon, all black holes look the same, but there's a gravitational redshift factor as you go out to infinity that makes it so the bigger black holes look like they have lower temperature out at infinity. Okay. So now, in this, to actually see the Hawking effect, we want to do quantum field theory on this curved space-time background. So, for the moment, let's just pretend we're doing quantum field theory where the quantum fields do not back react. So it's just, they're just like test quantum fields, because you can work out the temperature just from that. So we're going to, there's a special state called the Hartle-Hawking state that exists for static black holes. So the black hole is static if for that the killing vector with respect to which it is a killing horizon must be have a time reflection symmetry, and that means the black hole is not rotating. This omega would have to be 0. If the omega is, so like Schwarzschild is static, Kerr is merely stationary. That's the terminology. Now there is in a moment I'll say how close you can get to having a Hartle-Hawking state when it's Kerr. But let's start with Schwarzschild. So the Hartle-Hawking state, psi Hartle-Hawking, is a state that is obtained from a path integral It's the state that is obtained if I just take my black hole state. This one's asymptotically ADS, just to mix it up, and I do a Euclidean path integral by going in the by analytically continuing this in the perpendicular direction. So I just analytically continue whatever boundary conditions I have if it's ADS, and then I just do the path integral up to any this Cauchy slice, and that path integral, since I've specified my boundary conditions, that's like specifying an initial case, or in the case of something like de Sitter, there would be no boundary, which is just as good. I end up with a state, a quantum state that's pure of what I'm going to call the outside and the inside. Everyone agreed with that? So it's obtained from this Euclidean path integral. Now this state has a number of interesting and important properties. So the first property, one property is that if I restrict this Hartle-Hawking state to just one side, the side I've arbitrarily, make this agree with my notes. I've arbitrarily, but to agree with my notes, the inside is the left side, and I've called the right side the outside. If I now take the density matrix version, the mixed state, that is formally defined. Ed has been talking about the more rigorous algebraic way of doing this, but I'll just be sloppy here by tracing out the inside state. Like this. Then this state is a thermal state, which means that it's given by e to the minus a modular Hamiltonian k, where k is given by 1 over the temperature times an integral over any Cauchy slice in the space-time of the stress tensor contracted with the killing vector and the natural measure associated with the Cauchy slice. So this is the killing energy. That's the same regardless of which slice sigma you evaluate it on. This is a pretty important construction. Because it's the energy canonically conjugate to this killing time translation. And one good thing to know about why this works is that the stress tensor is conserved is conserved locally in general relativity, but because it has two indices, it's hard to write down a good gravitational Gauss law that makes sense globally. But if I have a Killing vector, then what I can do is I can contract my stress tensor with the Killing vector, and now this is like a one-index object. It's like a current, and I can say that if I take the divergence of this current, that is equal to 0. And the reason why that works is because this derivative either lands on the stress tensor, but that's conserved, or it lands on this, but then I get TAB times this. And because this is symmetric, I can make this guy symmetric too. And that's 0 by Killing's equation.
Aaron?
Yes?
Sigma in the integral, that's half of the sigma over there?
Yeah, in this case, the global Killing energy, of course, of the whole space-time would be defined without that caveat. But as used in this formula, I mean the Killing energy, particularly of the outside. So possibly, I should say sigma out here. And then the statement is that this is going to be the same for any partial Cauchy slice that's a Cauchy slice of this outside wedge here. That will always go to this bifurcation surface. Was there another question? Okay. So this is in some sense the Hawking effect, although we need to be a little, this is in a black hole that's in an equilibrium state. So,
Clarification question?
yes.
In the diagram on the left, the plane that's coming out of the board, is the integral infinite to one side? Is that how direction?
If it does whatever the Lorentzian spacetime did, in this case, this bar represents the conformal infinity of ADS.
No, I meant the Euclidean slice.
And the Euclidean slice is the same. It also goes out to infinity. It's a hyperbolic space, because Euclidean, the Wick rotation of ADS is hyperbolic space, which is conformally like a disk. We could have done this with asymptotically flat too, but it's a little harder to draw. So, but the point is, because you're analytically continuing, whatever boundary conditions you have here is determined by what you are doing in Lorentzian symmetry. And to get this Hartle-Hawking state, it was important that we had this boost Killing symmetry, because that's what gives you the rotational symmetry of this path integral that gives you this thermal temperature here. So the Hartle-Hawking state, it's important to know, represents a black hole that's in equilibrium. Yes? You go all the way to infinity. Go all the way to infinity and impose whatever reflecting boundary conditions are the analytic continuation of the boundary conditions that you wanted to impose on Lorentzian signature. Yes?
So the temperature shows up in the radius of curvature of the hyperbolic space.
Well, this is the Schwarzschild ADS is asymptotically ADS, but the black hole is a deviation from ADS that's in the middle. So this is some Euclidean space-time that's asymptotically hyperbolic, but it's not. It has a different curvature in the middle associated with the black hole. the temperature shows up in the ratio between how much angle you have at infinity and how much you would have at this boost going around. This is like the Euclidean black hole is like a sort of cigar-shaped geometry. And so the 2 pi angle here corresponds to some variable-sized thermal circle out at infinity.
But that's the cigar is the asymptotically flat case in the Penrose diagram.
Right. So this is, because this is asymptotically ADS, it will spread out. And there you have to deal with the fact that we also have a redshift divergence at the boundary. So when I talk about the temperature at infinity, I'm either putting in a cutoff or somehow rescaling it as I take that limit to the CFT time. Yeah. But none of this is particular to ADS. It's just the example I perhaps foolishly chose to draw out. Okay, so there's another property here which is less well known, but is important for, oh no, I was going to say the black hole is in equilibrium with its Hawking radiation. So this Hartle-Hawking state actually represents, it's not evaporating black hole because radiation is coming out both in and out. It's surrounded by a cloud of gas that has the same temperature that it does up to the, I mean that in the sense that's related by redshift. So one thing to know is that if you wanted to describe an evaporating black hole, you would not use the Hartle-Hawking state. You would use a different state that's called the Unruh state, where what you would say is that the radiation coming out from the black hole is the same as in Hartle-Hawking, but you say that you have the vacuum state coming in from past infinity. That state will lead to a net flux of energy coming out, but it is not as nice of a state in that it has it's not regular on the past horizon. So it's got the quantum fields, their 2-point function will blow up badly in a way that would give a sort of infinite spike of energy on the past horizon. That doesn't matter if this black hole formed from collapse, because if the black hole formed from collapse, these two regions aren't physical. The star that collapsed will be there, and it's just these two regions that we have to worry about. There's also a state called the Boulwar state, where the black hole isn't radiating at all, and it's just a 0 temperature state, but that's singular on both horizons. So the Hartle-Hawking state is a state that's a valid state of the quantum field theory on the whole eternal space-time. Yes?
So these different states, would it correspond to just choosing different boundary conditions in the big picture on your left?
No, because I defined the Hartle-Hawking state from a Euclidean path integral, but it's not, well, you could probably define the Boulwar state by taking this angle to be infinity instead of going around 2 pi. But the Unruh state, I believe, is going to be very difficult to define in Euclidean signature. You really want to define it in Lorentzian signature because the boundary condition, the vacuum condition is naturally imposed on past null infinity here. So Euclidean path integrals are just tricks for getting particular states. That's all they are. you can have a state that may not come in a nice way from a Euclidean path integral. Yes?
Is the Hartle-Hawking state the only one that's invariant under the Killing symmetry? Is there a statement like that, or is that not?
I seem to vaguely recall that that may be a theorem, but I wouldn't swear to it. Actually, no way. In the case of a free quantum field theory, I could prove it.
So the Boole state is not invariant under the...
Sorry, I mean, we're talking about regular states when I say
Oh, I
this.
see. I see.
The Boole state is invariant. If you don't care about regularity on the horizon, you could make the quantum fields have any temperature you want. You can just adjust the knob. But regularity on the horizon makes everything, fixes the temperature. Okay, so the second property of the Hartle-Hawking state that is less well known is, I'm going to write down the pure one, that this state is a vacuum state on, I'll just say the future horizon, although there's of course a time reversal statement on the past horizon, with respect to the null translation of generators. So Ed actually ended his talk by talking about these symmetries that generate the annex that has a null coordinate. He wrote u, but I'll write v. It goes v plus f of the transverse directions y. And these are associated with the average null energy integral along each generator. So this thing equals 0 on each generator in Hartle-Hawking. So it's 0 in Hartle-Hawking. And it's acting in the Hartle-Hawking vacuum. That's what I'm, sorry, what are you? Oh, sorry, I mean, I was writing this somewhat naively, but I mean this. That's what I meant by in Hartle-Hawking. So actually it's not just that it's 0 on average, it's exactly 0. And that follows from the fact that we know from the average null energy condition that it's actually greater than or equal to 0 in all states. And therefore, although we could easily have derived that the expectation value is 0 just by using a boost argument, by sort of dimensional analysis, it's the only thing that makes sense. This, because we know that this is non-negative in every state, if the expectation value is 0, it cannot be because it has quantum, it's like some Gaussian or something that's sometimes negative and sometimes positive. The only thing it can be is exactly a 0 eigenvalue. So in particular, because it's the lowest energy with respect to this translation, it's actually a ground state. Maybe a ground state would be a clearer thing to say than vacuum state.
So you're not claiming the proof directly from the path integral?
I am not. I think it's easier actually to go in the opposite direction and to say that once you've defined the ground state of the once you've defined that you're on a ground state then to get that at least the state looks thermal on this horizon would be an analog of the Biesiano-Wickman theorem that says if you have a ground state with respect to the energy and then you also have a boost-like symmetry, then the you'll get a thermality property. This is what Sewell did in his derivation of the Hawking effect. But the fact that this looks like a ground state is a very classic result in black hole thermodynamics that was proven by Israel and Kay and Wold and a bunch of other people. Okay, I should say, I think Ed mentioned this as well, but this V translation symmetry can move you across the bifurcation surface. It's not a symmetry of the space-time, it's only a symmetry of H+. So this is a funny sort of near-horizon symmetry.
Sorry. Here's the question, how do we know that Anak is satisfied in this bulk setup? We only proved it for like flat space or something. A lot of the proofs are discussed in flat space, but the recent proofs by various people named Tom, I think, could be extended to this case without too much difficulty. If you have free quantum field theory, then one thing you can do is identify the Fock space on H+, and then the fact that in that framework, the fact that the ground state satisfies the average null energy condition is actually manifest. It just comes from writing it in terms of creation and annihilation operators and showing that it's a sum of manifestly positive A-Dagger A type things. So this is a theory of gravity, right? Not just a QFT.
No, we're talking about a quantum field theory. Right now, we're talking about quantum field theory in curved space-time. So it's not, the quantum fields don't yet back react, although we'll throw that in later. Actually, if we did let the quantum fields back react, in a lot of situations we'd be in trouble because the Hartle-Hawking state has an infinite. Say I have the Hartle-Hawking state of a black hole in asymptotically flat space-time. It's sitting in an infinite realm of gas that's all at a constant temperature if we're far enough away from the black hole, and such a thing is itself inside its own Schwarzschild radius and unstable to gravitational collapse, and would actually mean that you have to be in the cosmology instead of asymptotically flat. So it's you have to be a little careful. Okay, so. Yes.
So that integral from minus infinity to infinity.
Yes.
It's split it in, say, 0 to infinity because it's probably symmetric the other way. And then if the integral is from 0 to infinity.
Sorry, no, it's not. It's not. Sorry, the integral from 0 to infinity. You're saying specifically in the Hartle-Hawking. Well, in the Hartle-Hawking state, actually, there's a stronger statement that's not completely stronger. All right. In the Hartle-Hawking state, it is also true that the expectation value of TVV equals 0 everywhere on the horizon. So if you don't mind putting an expectation value around this, you could take it from 0 to infinity. However, in that case, it will have infinite fluctuations. And so the things I was saying about it being like a ground state will no longer be true. Does that, I didn't actually listen to your question. Let you finish your question before I gave the answer, but does it answer it?
No, what I was wondering is that the Hartle-Hawking state can be, the way you prepare it using the Euclidean path integral is similar to the preparation that we do in flat space with the Minkowski vacuum, and how you evolve it to minus infinite time.
That's right. In fact, this could have been the Minkowski vacuum, and everything I'm saying is still true.
And that prepares the vacuum state. But what's special with the Riddler guys, because he only sees the right-hand side, and therefore he sees the thermal state. So I was trying to see now, like, what if an observer just starts from, because over here, if you think of an observer starting from, say, from minus infinity to plus infinity, he only has access to the right-hand, he never sees the left-hand side. So if PU is integrated from minus infinity to infinity.
So this is going from here to here.
Yeah, so he never has any access to the left-hand side.
Yes.
So I was just wondering why does he still see a vacuum? Because
Oh, yeah, I see your question. It's because the, so if you remember when Ed was talking about the proof of the Riesz-Leiter theorem, he said that your region has to not be too large, meaning that it has to be space-like separated to an open region. And this entire generator of the horizon that goes from minus infinity to plus infinity actually is too large for the Riesz-Leiter theorem to apply to it. Because it does, it doesn't, it's not going to have an open set of things that space-like too. In that sense, it can see almost the whole space-time, either by shooting to the past or to the future. Okay, so the third thing I was going to tell you about the Hartle-Hawking state, which I'll be brief about because Ed already said it, is when you restrict to the region above any cut, rho Hartle-Hawking, by which I mean restricted to that region, is by which I mean restricted to the wedge outside of that cut, is still a thermal state. With respect to the following modular Hamiltonian. I want a picture here. I'm going to draw it here. So here's the generators of the horizon. Here's some cut. I have a v coordinate. That's the null coordinate. And I define my cut by some function v equals v star of y. Okay? So v star is my cut. Y is my transverse directions. The modular Hamiltonian as a function of this cut is given by something that looks like the Unruh modular Hamiltonian. And this is an integral above the cut of the future horizon that says dv v minus v star tvv, and then integrated in the d minus 2 transverse directions. This is v. Okay. So the thing about this is if we took v star equals 0 to be the bifurcation surface, this is just the formula for the boost energy falling across this horizon, because the boost energy is like an energy times a position, but in the null direction it's just tvv times v. Here, we modify that by just shifting by a translation, so we just look at this is sort of our pivot point, and this is the thing that generates a sort of dilation around this. Plus, so there's sort of two cases here now. One case is when we have a space-time like Rindler in d greater than 2, or like ADS, where we can anticipate that all information will eventually cross the future horizon. In that case, we just need to write this down. The other case is if we're asymptotically flat, there may be some stuff that heads off to infinity that never crosses the null surface. If we're in that case, that stuff has a modular Hamiltonian too. That is just associated with the killing energy of stuff that goes off to infinity. So this is the contribution from Scribe Plus. Okay, but the thing about this term is that it is V star independent. So if you want to know, this is just the same regardless of the value of V star. So if we're comparing two different cuts, we don't care.
Can V star be negative?
Yes, absolutely. And then the cut can be down here, or it could even be a wiggly cut that's positive in some places and negative in others. Okay, now, yeah.
Sorry, I don't understand why is this term.
Why is this there? I didn't prove it, although Ed almost did in his last talk. It's because, actually I can sort of derive it from 1 and 2 together. Because this is a ground state, it has a null translation symmetry that moves the location of this cut. So if I put the cut at the bifurcation surface, then I know the Hartle-Hawking state is thermal with respect to this V star is 0. And if I now translate my cut, then I must have the null translated formula. Okay. Yes?
For general field theory, how general theory in this curved space, how can you show the second naked?
How general?
I mean, for general field theory, how to show the
Yes. So that's the other comment I should mention, is when I originally proposed this, I could only show it for theories that were free in the ultraviolet, but actually there's a paper now by Cassini, Teste, and Torriba where they proved it more generally for anything that flows to a CFT in the ultraviolet will obey this exact same formula for the modular Hamiltonian. Strictly speaking, we're looking at the case of Minkowski, where this term isn't here, but I would be extremely shocked if it didn't work exactly the same.
I'm asking the second formula.
Oh, this formula. Yeah, that's true too. That essentially follows from the fact that the average null energy condition has now been proven by people named Tom for every field theory. Yes?
If you have a one-sided black hole and you continue one of the geodesics like back in time, so it's no longer on the horizon at some point, but you still defined like this TVD, so you now have an operator that's positive because you have infinite extent in both directions. Can you find some state where it's going to
So that's not going to work because if the black hole formed from collapse, the generator, well, you could follow the generator to back before it was in the horizon. It will not be achronal. And therefore, there's no rule that the average null energy condition holds on it. If you have the most convenient thing to do with a black hole that forms from collapse, assuming you've let it settle down to a nearly stationary case, usually you can analyze, as long as you don't care about the collapse process itself, the best thing to do is to just pretend you're on the eternal black hole space-time and just bear in mind that whatever state you're looking at is only valid above a certain value of V star. That works pretty well. Okay, now I want to say before we move on away from the Hartle-Hawking state, I want to explain why there is no Hartle-Hawking state for the Kerr black hole. And that is because if we look at this formula, in the case of the Kerr black hole, so this still looks locally like a boost. And so we can still define a temperature and an Unruh effect, and there's Hawking radiation coming from it for the Kerr black hole close to the bifurcation surface. The difficulty is that if you remember what a rotational killing vector looks like, a rotational killing vector grows linearly. Just think about it in Minkowski space. A rotation grows linearly in its size as you move away from the origin. whereas the time translation symmetry just stays the same. What that means is if we get far enough away from the Kerr black hole, then the killing vector is going to become space-like. And if it's space-like, there can be no thermal state defined with respect to it because the killing energy is unbounded below. This is related to the fact that Kerr black holes have superradiance, that you can do the Penrose process to extract mass from them even classically, and a bunch of other things. However, it's not really a problem with the horizon itself because the killing vector only goes space-like when you get far enough away from the black hole. So if, for example, you imagine putting the black hole in some kind of box, which could be in ADS space-time, and if the box is sort of close enough to the horizon that the killing vector doesn't become space-like, you've still got a Hartle-Hawking state even for Kerr. Or, more generally, if all you want is a state that looks like the vacuum ground state on the horizon, you can also find that, if you don't mind that it's not going to be exactly thermal out at infinity. It can still look just like the Hartle-Hawking state here. So technically, the Hartle-Hawking state doesn't exist except in special situations. Conceptually, it's not as bad as you might think. Okay. The next topic is the Bekenstein-Hawking entropy. And I guess we start here. Okay, so you've seen this. So, but why? Why do we believe that this area is an entropy? Well, now there's lots of reasons, but if we look historically, two of the reasons are, so Ed just proved for us the Hawking area increase theorem. So we know that A increases classically, like an entropy should. That does not yet fix the coefficient. This is assuming the null energy condition. But another thing is something called the first law of black hole thermodynamics. And this is the statement that looks very similar to the Clausius relation of thermodynamics that says dm equals TdS. And if we've got rotation, we have to add some work terms that are annoying and aren't really important if you're localizing yourself near the horizon generators. You can sort of ignore that, but are important for relating you how quantities go from infinity to the horizon. So what you notice, so actually the whole subject of black hole mechanics, Bekenstein noticed this analogy before Hawking radiation was discovered, but he couldn't fix the constant proportionality. Hawking radiation tells us what this temperature is, and that also lets us fix the constant proportionality with the entropy. The first law can actually be interpreted in two different senses. You could think of it, there's a stationary comparison version where you take two infinitesimally close black hole solutions and you compare their parameters, their intensive and extensive parameters using this formula, and it works out. There's another more exciting version called the physical process version where you start with a nearly stationary black hole and then you throw in a little bit of matter and you let it actually dynamically evolve to a new black hole configuration with slightly different mass and area and the rest, and that also satisfies this. you can prove that, at least given the assumption that the black hole does eventually settle down instead of blowing up. But
The
yes.
second one should only work as an inequality, shouldn't it? You have to be quasi-static.
As I say, it has to be close. So it's for a first order perturbation to the fields. But when I say first order, that allows us to do a first order sized contribution of the stress tensor, even though the stress tensor may be second order in its fundamental fields. Okay, so but yes, that is that you have to be quasi-stationary. This is sort of a close to equilibrium notion. That's a fundamental limitation of the first law that is not a limitation of the second law. In his proof of when he proved the area increase theorem for you, Ed never said that the horizon had to be anywhere close to stationary. He was considering mergers and that sort of thing. Okay, and now we come to the part of the talk where you watch me move blackboards up. It's everybody's favorite part. You can take a little breather, chat quietly with the person next to you. Okay. Oh, this one I can do myself. All right, I'm going to talk about the corrections to this Bekenstein-Hawking formula when there's quantum and Striggy effects. Okay. So the corrections are of two different kinds. First of all, we have quantum / thermal corrections. So it's quantum / thermal because, as you know, the Hawking effect comes when you have quantum mechanics and it's thermal, so these are all sort of the same thing. So one could justify this in a rather naive way and say if I have a black hole and that has entropy, and I also have some quantum field configuration outside of it and that has entropy, if I want the total entropy of the whole universe, I should add them together. Now that's actually more mysterious than you might think, because somehow this area of the horizon is, we don't count, that counts the whole entropy of the black hole somehow, and we don't count any matter that's inside the horizon. But what we do is we define the outside entropy as minus trace rho out log rho out. So this is the formal definition of the von Neumann entropy, where rho out is the quantum field theory state outside of some cut. And now we will define a generalized entropy is going to be equal to the expectation value of the area now over 4gh bar plus this outside entropy. So this is a sum of two terms. And we need to take the expectation value of the area because the quantum fields are going to back react on the geometry, and that back reaction is going to affect the area at the quantum level, at the quantum operator level. But S out, you notice, is not an operator. It's just a function of the state rho. And so we need something else that's a function of the state rho, and we take the expectation value. You could actually justify that more convincingly by saying if you knew that the black hole really had e to the a over 4 states and was in a maximally mixed state, but then you consider the state where it was in a superposition of, or a mixture of two different such states with different area, you'd end up wanting to use the expectation value of the area. So the reason why back reaction is important, the quantum effects like Hawking radiation or the effects of some order unity number of quanta, the energy of a quantum is h bar omega. So the stress energy tensor is going to be proportional to h bar. The gravitational effects are going to be proportional to gh bar. But there's an over gh bar in the denominator here, which means that the quantum corrections to this term are actually of order unity, the same as this. So you got to think about them both.
So Aron,
Yes.
we're doing classical gravity coupled to quantum.
Right, so we're doing semi-classical. At the moment, we're doing semi-classical gravity. So what that, you could take that to mean that we have we're sort of doing an h bar or gh bar expansion where we have a 0th order piece of the metric, and then we have a back reaction piece that's an operator that's like a 1st order piece. And then if you are brave enough to actually quantize linearized gravitons on the background, there's actually a order 1/2 piece, because the energy of a graviton is of order h bar, but the energy of a gravitational wave goes like its amplitude squared, and therefore its amplitude goes like square root of h bar. But this ultimately just contributes quadratically to this stuff in much the same way matter does. So if you're doing something like the generalized second law, this is the thing that increases. And you could say, assuming that the classical black hole is classically stationary, you can then evaluate at the order 1 terms whether it's going up or not. And it will, yes?
Do you assume that the variance of the matter stress tensor is small?
You do not need to assume that when you're dealing with linearized back reaction perturbations. If you have, so this raises the question of the semi-classical Einstein equation. A lot of people write down something like GAB equals expectation value of TAB. And this is sort of a bogus equation most of the time, because this thing could have variance. And if, for example, you do, if the Earth has a wave function that's spread all around the sun, you're not going to be equally attracted to each term in the wave function. You're going to be attracted to where the Earth actually is, not where it could have been. So I hope I made every interpretation of quantum mechanics unhappy with what I just said. But there are a couple situations, I know of a few situations where this is justifiable. One situation is where you have a large number of quantum fields, and then the variance goes like square root of n, but the expectation value goes like n. Another situation is, for example, if you have a black hole that's Hawking radiating for a very long period of time, then again things average out because there's a large amount of time. But My favorite justification is to say I believe in this as an operator equation, and then I can take the expectation value of both sides. And then I can say, as long as I'm only dealing with linearized perturbations to a background, I don't have to worry about the bothersome fact that expectation value of AB is not equal to the expectation value of A times the expectation value of B. As long as I only deal with first order quantities and I'm ultimately just calculating this expectation value, it'll work out. Okay, so, yes?
So for the gravitons, linearized gravitons, are they also in Hartle-Hawking State?
So for the linearized gravitons, you should not use this, you should not do it the way I just said. You should treat them as if they were a genuine quantum field and then work out the expectation value of the stress energy tensor-like thing that is the quadratic in them. But it works much the same way matter does. If you're doing the Raichaduri equation, then actually the shear squared term behaves much as if it were the null-null stress energy tensor for the graviton. There's a nice paper by Candelas and Sciama talking about the Hawking effect for gravitons that goes into this. Okay. Yes?
Is the effect of the gravitons to be considered in the S out that you have written?
Yes, it is. They also have a von Neumann entropy. And that's important if you are keeping track of Hawking radiation of gravitons. So I want to say is each of these terms can go down separately. For example, if the black hole Hawking radiates, the area will go down, but the radiation outside will carry the entropy more than that, go up by more than that amount. Whereas if you dump something into the black hole that has entropy, the entropy outside goes down, but the area increases. That's called the generalized second law. But there is, I'm going to prove the generalized second law in detail next time. What I want to say now is you should be worried about whether this is even defined, because as other speakers have told you, the von Neumann entropy is divergent, so this is actually equal to infinity. So there's various games you can play when you're just talking about entanglement entropy and field theory to try to extract the universal coefficients. But here we play a different game, which is renormalization. So what we do is we add counter terms to absorb the divergences. The leading order divergence is proportional to the area, so it looks like it should shift the value of 1 over Newton's constant. That turns out to be how it works. So to study this in more detail, we actually need the second kind of correction, which is higher curvature slash stringy slash counter terms corrections. And the way these work is we have a gravitational action that I always write as I because S is taken in this subject. That's an integral of the Lagrangian, where the Lagrangian has an Einstein-Hilbert term, but then it may also have corrections that involve various powers of the Riemann tensor, maybe some derivatives as well. So these are various scalar corrections, like the Gauss-Bonnet term that Matt mentioned. And in the area, the Bekenstein-Hawking formula is only valid when you're in Einstein gravity. But there are loop corrections in quantum field theory that generate not just the Einstein-Hilbert term, but also other higher order things. For example, in 4 dimensions, a free field will have log divergences contributing to things that look like various contractions of the Riemann tensor with itself. So to deal with that, we need a formula for the generalized area functional that results from that. And there is such a formula which can be written y is the transverse directions, remember, and then in null coordinates for simplicity, so I have a v and a u, and then I and j will be things like the transverse directions. There's a term that's called the Wold Entropy that involves differentiating the Lagrangian with respect to the UV component. So this is the Wold Entropy, and it was derived based on, it was proved that this formula obeys the first law. So it's valid when the black hole is stationary, and it also gives the right answer when your action is f of r gravity, where f of r is some function of the Ricci scalar. But it's not valid in general, and the reason why it's not valid in general is the Wold and Eier method for deriving this higher curvature entropy, which was essentially based on properties of the Killing field and requires the black hole to be stationary. When the black hole is not stationary, there are some ambiguity terms that appeared that were first discussed by Jacobson, Kang, and Myers. And those ambiguity terms are basically anything you could write down that vanishes when the black hole is stationary. Now, so an example of that would be things involving extrinsic curvature. So I could write down an ambiguity term with the extrinsic curvature of a codimension 2 surface. Our extrinsic curvature has 2 indices along the surface and 1 normal direction, because it can bend in either, say, the u or the v direction. And if I take the product of the u extrinsic curvature with the v extrinsic curvature, this is boost invariant, as the entropy should be, but it vanishes on a stationary black hole because each of these things, the factors are not boost invariant, and therefore they're 0 on a Killing bifurcation surface. On H plus or minus, one or the other of these will be 0. So these ambiguities were not resolved until recently, but we at least know the next correction now, and that was due to, like, for example, the work of Persayev, Patrushev, and Solodukin in quadratic curvature gravity, and more generally the work of Xidong, who derived this formula for holographic entanglement entropy, but also has applications to black hole thermodynamics. So here's the expression, just so you can see it and know it's there. So I have 2 more copies of the Riemann tensor. This could have been contracted in a number of ways, and fortunately, it turns out to be contracted in the way that's easy to remember. The Riemann tensor with 2 u's has an ij index, and that matches to the k that points in the u direction, and the one that has 2 v's has k and l, and that matches with the k that points in the v direction. So this is FPS, Dong, Camps, some other people. And then this is known up to, there's higher order corrections of order k to the 4th and so on that are still ambiguous. Now, this stuff's all recent. For stationary black holes, people have been studying this since the 90s and have worked out that this renormalization story does seem to all make sense. So, yes?
Are we assuming that the Lagrangian doesn't depend on derivatives of the Riemann tensor?
This formula does. However, if there are derivatives, there will be corrections. Actually, the Wold piece, you just do what you do as if you were doing a variation where you end up pulling a derivative out. But I believe the story for derivatives in general for these correction terms is not known for all actions, but Rongshin Miao has worked out some specific cases.
So here, this term is not ambiguous, or
This term was calculated by methods that resolve the ambiguity. And I'll say in a future lecture, I'll tell you something about what those methods are. But I don't have time for it now.
is it known if you have like transscience terms in the gravitational action?
Yeah, you have to modify the formalism a little bit, but it works out. There's somebody's done it.
So have you considered the boundary terms in the action? Is that necessary to consider it?
No. If you mean things like the Gibbons-Hawking term, they tend to cancel out because when you calculate the entropy, anything that is, it's terms involving curvature that depend on a conical singularity at the horizon that matter. Anything that just would linearly grow as I change my beta on the boundary ends up dropping out of an entropy calculation. And that's why we get something that's local on the horizon. So now the way renormalization works is that, yes.
You said the Wold Entropy basically only works for f of 3g scalar?
And for stationary black holes.
And for stationary, okay.
Yes.
So stationary works for what?
Yeah, for both those cases. It sort of had to work for f of r because that's field redefinition related to gr. All right, so I should at least say, so we have renormalization. The point of renormalization is that it's neither of these two terms really make sense on their own. It's the combination of all of it that ends up being cut off independent. So what I should really do is I should really write my generalized entropy as a function of so the generalized entropy depends on Newton's constant. It depends on 1 over Newton's constant. That depends on my cutoff because there's loop corrections to Newton's constant. And it also depends on other parameters in the action that are also depend on your cutoff. They have non-trivial RG flow. But there's also an entanglement entropy divergence, and that depends on the cutoff. And the statement is that as long as I regulate both of these terms in the same way and send epsilon to 0, this is going to be cut off independent. So that means this is actually a UV finite quantity, and we've therefore learned something about the black hole, some finite UV quantum gravity quantity, just by thinking about the semi-classical physics. So it's of course believed that this tells us about some actual state counting of some finite number of degrees of freedom of the black hole. So the hypothesis is that black hole entropy is statistical mechanical, and that it counts the degrees of freedom that are somehow at the Planckian structure. So I was going to say more about that, but because I'm out of time, I will actually save the fact that this is the same as this induced gravity scenario for the next time, and we can go to questions.